Hello, my name is Renata and I will present this work named Predicting Soft Robots Locomotion Fitness. I did this work together with my advisors Dr. Fujita and Dr. Takahashi. In our work, we want to find the shape and dynamic principles of an organism's body that can predict locomotion performance. Organism's locomotion, and the organism could be a robot or an animal, is an emergent phenomenon of its body and environment. There is a diversity of body shapes and dynamic strategies that generate locomotion. We are studying specifically locomotion in a hard ground environment with no obstacles. For example, all these and these robots are different and are solutions that locomote in our environment. We want to find general principles in them that are related to their ability of locomotion. We choose to perform a simulation study of voxel-based soft robots using the physics-based engine Voxelize. We use an evolutionary algorithm as a way to generate a large sample of robots without having to do any assumptions about the solutions. We are analyzing the robots using statistical mechanics principles like phase transitions and renormalization. We studied first the 2 to the power of 3 space, where robots can have up to 8 voxels. We simulated this space exhaustively, evolving a population of 50 robots up to 2,000 of generations. Then we grouped the robots into shapes. Here are some of the examples of shapes. Each shape contains robots that have the same voxels after reflection and rotations in the XY plane. Here, we have the results of some basic features of the shape, the number of voxels, and the number of voxels touching the ground that we called feet. Each of these squares represents a shape and it is colored using the maximal fitness that a robot of this shape has acquired. These results show that in most cases, a large body is better, or it is better to have 2-point contact with the ground. We are also analyzing the dynamic features of the shape. There is a global sinusoidal signal that controls the actuation of the active voxels. Each voxel can have an independent phase offset value in relation to this global signal. Here, we select some of the better and very different shapes. They are the same as this figure here. Each one of all the robots that belong to each of the shapes is plotted here. And we calculated the absolute difference in the phase offset of the extremal voxels of the body. In this example of the shape 16, the most distant voxels are these two. And we calculated the absolute difference of phase offset between them. We plotted this number in relation to the fitness of its robots. We can see that even for very different robots as 16 and 6, the robots with better fitness have an X value close to 0.5, which means close to pi radians. And here we plot together results of 2, 3, and 4 up to the power of 3 dimensions. In each generation of our evolutionary algorithm, a parent is mutated, generating a child. On the bottom 3 plots, the color code represents the log of the number of times each of these transitions happen. For example, the transition of a parent with 4 voxels to a child with 4 voxels. The top 3 plots have as the color code the mean value of the difference of fitness in each transition. They show that, on average, phase transitions that increase the number of voxels, here, here, and here, have a positive impact on fitness, while decreasing the number of voxels has a negative impact on fitness. Our work shows that there are relatively simple morphological and dynamical characteristics that can predict locomotion fitness. These initial results indicate some features that the evolutionary algorithm selects during its optimization in our simulations. Thank you for your interest and attention, and if you need, my email address is available in the full paper.